take a look around you, at the stainless steel you interact with every day. I mean, the shiny kitchen sink, the pristine surgical tools at your local hospital, or like those massive high-pressure valves in a chemical plant.
Yeah, they just look flawless.
Right. There is this total expectation of perfection. It just looks engineered, clean, almost, effortless. But behind that smooth, indestructible surface is this brutal, high-stakes war of physics that almost nobody sees.
Oh, it is absolutely a war. It's a microscopic, incredibly violent clash of engineering, heat, and pressure.
Which is wild because we look at the finished product and just assume, that it was easy to machine.
Right, but the thermodynamics happening at the actual cutting edge would completely blow your mind.
Exactly. And that is why we are here today. We are doing a custom deep dive designed just for your curious brain, looking at the exact hidden engineering battles happening every single day to create the stainless steel objects you rely on.
Because it's a massive challenge.
It really is. The specific focus of our deep dive today is the challenge of machining ISO-M stainless steels. And actually, there's a quote from Albert Einstein in our source material that sets the tone perfectly here. In the middle of difficulty lies opportunity.
Oh, that's incredibly fitting for this topic.
Right. Because when you look at the stubborn, unyielding nature of modern metalworking, difficulty is basically the baseline. Okay, let's unpack this. Why are we focusing on this specific type of steel? Like, why should you care about something called ISO-M?
Well, you should care because austenitic stainless steel, which is the primary material in that ISO-M category, it makes up more than 70% of all the stainless steel used worldwide.
Wait, 70%?
70%. I mean, from the cutlery in your drawer to massive deep sea oil rigs, it is literally everywhere. But here's the catch.
There's always a catch.
Always. Despite it being everywhere, the actual process of shaping and machining it is a massive engineering hurdle. It's this invisible struggle that the average person is completely blind to.
The invisible struggle. I like that. But, to really grasp how we shape the world's most common stainless steel, we first have to understand how engineers categorize it, which, interestingly enough, takes us on a weirdly fun detour into mid-20th century German technical terminology.
Yeah, the ISO 513 standard.
Right, because those letters aren't just random, are they?
Not at all. The ISO 513 standard is essentially the foundational rulebook for machining applications. Back in the day, engineers needed a systematic way to group metals based on how they behaved under a cutting tool.
Specifically looking at the chips, right?
Exactly, the physics of chip formation.
Yeah.
How does the metal shear away when you cut it?
And so they came up with 3 original identification letters. First, you had P. This stands for the German word plastisch, meaning plastic or ductile.
Right, and in the context of machining, ductile materials, like your standard carbon steels, they undergo plastic deformation before they shear.
So they kind of stretch and flow.
Yeah, when a tungsten carbide cutting edge pushes into them, the material flows over the top of the tool, producing these really long, continuous chips.
Got it. Then, on the complete opposite end of the spectrum, you had the letter K. That comes from Kurse, which is German for short. These are your highly abrasive materials, like cast iron, right?
Exactly. When you cut cast iron, it doesn't flow at all. It fails through abrasive fracturing.
So it just breaks.
Yeah, the material just kind of crumbles and snaps off under the pressure of the tool. It leaves you with these tiny, short chips.
I was actually trying to picture this, and it kind of reminds me of sorting types of wood by how they splinter when you chop them.
Oh, that's a good analogy.
Like P materials are like chopping a green, sappy pine branch. It peels off in these long, stringy strips. But K materials are like chopping a piece of dry, brittle particle board. It just turns into chunks and dust.
That is exactly how it works. And the mechanics of that chip formation dictate everything about how you design the cutting tool. I mean, from the rake angle to the clearance. If you don't know the chip style, you just can't design the tool.
But then we have the third category, the one we were talking about today, the letter M. This stands for middle, the German word for middle, or Misch group, the mixed group.
Right, the in-between material.
Yeah, this group shares characteristics with both the long chipping P steels and the short chipping K metals. But I have to push back here for a second.
Okay, go ahead.
If M just means middle or mixed like a catch-all category, why did austenitic stainless steel basically take over this entire classification?
What's fascinating here is that the M category wasn't originally meant to be synonymous with just one specific metallurgical family.
It was just a mixed bag.
Exactly. But austenitic stainless grades, specifically the really famous ASI 304 and 316 grades, They became such an absolute standard for global manufacturing.
Because they're so versatile.
Right. They offered this incredible combination of high corrosion resistance, formability, and weldability. So because they became universally popular across almost every industry, they essentially swallow the M category whole.
Wow.
Yeah, when a machinist today sees the blue letter M on a box of cutting inserts, they aren't thinking about a mixed group of metals. They immediately think, austenitic stainless steel.
It's like Kleenex taking over the word for tissue. If you knew how to cut 304 and 316, you had basically mastered the M group.
For decades, that was entirely true.
But those good old days of just dealing with basic 304 and 316 are over, aren't they?
Long over.
Because our source notes that evolving industry demands things like deep-sea oil drilling, advanced aerospace components, next-gen chemical processing. They've forced metallurgists to create a whole new spectrum of metals. It's like a modern metallurgical zoo out there now.
It really is. The basic grades were fine for everyday applications, but the environments we are putting these metals into now are so extreme the metallurgy just had to adapt.
And that causes problems.
Huge problems. This new lexicon of materials is where the headaches for manufacturers really begin, because every time you tweak the alloy to make it survive the real world, you make it drastically harder to machine.
Okay, let's walk through this new lexicon because the names alone sound like superhero alter egos. First, we have super austenitic stainless steel.
So with this one, you take your standard austenitic base, but you pump it full of molybdenum, and you significantly increase the percentage of chromium and nickel.
And what does that do?
The result is a metal with extreme resistance to pitting corrosion. You can soak it in harsh chlorides like seawater or industrial chemicals, and the localized corrosion mechanisms just can't penetrate the alloy structure.
Which is great for a chemical plant, bad for a drill bit. And that brings us to duplex stainless steel, which sounds like an apartment building, but is actually incredibly complex.
Duplex is fascinating on a microscopic level. It features a two-phase metallurgical structure.
Meaning?
It is roughly equal shares of austenitic and ferritic structures mixed together. But think about what that means for a cutting tool.
You're cutting two different things at once.
Exactly. You are essentially weaving two different types of metal together to get the yield strength of ferritic and the corrosion resistance of austenitic.
Wait, if you have two different microscopic structures mixed together, wouldn't that cause absolute chaos when you try to cut it? Like you'd be hitting a soft pocket, then a hard pocket, thousands of times a second.
Exactly. You just hit on the exact reason duplex is a total nightmare to machine. The cutting edge is constantly experiencing these microshocks as it passes through the alternating phase boundaries of the metal.
That sounds destructive.
It is. It causes severe vibration and highly localized wear on the tool.
And if that wasn't enough, we have super duplex.
Right, so take the duplex two-phase structure and just load it up with even more chromium, molybdenum, and nitrogen. The yield strength and corrosion resistance go completely off the charts.
Finally, we have heat-resistant austenitic stainless steel.
Built for the inferno. It is specially designed to maintain its mechanical properties and resist oxidation at massively elevated temperatures. We are talking above 600 degrees Celsius or 1112 degrees Fahrenheit.
That's insanely hot.
And it is so heavily alloyed with chromium and nickel that its properties actually start to overlap with the ISO S group, which is usually reserved for high-temperature aerospace superalloys like Incanol.
Okay, here's where it gets really interesting. When you look at these incredible new supermetals, there is this staggering engineering paradox in the text. The machinability rating of super duplex can be half or even less than that of standard AISI 304.
Yes, it drops off a cliff.
We have designed metals that are so incredibly durable, so resistant to their environments, that they are becoming nearly impossible to manufacture in the first place. It's like we've made the perfect material, but we can't actually shape it.
It's the ultimate double-edged sword. Every element you add, whether it's nitrogen for strength or molybdenum for corrosion resistance, actively fights against the cutting tool. You are asking a machine to effortlessly carve through a material that was specifically engineered to be indestructible.
Let's get into the actual physical clash then. The physics of the fight. When a tungsten carbide cutting tool spins up and smashes into a block of ISO-M stainless steel, why does the metal fight back so hard?
Well, if we look at the core physical challenges, there are basically 4 horsemen of machining M group.
Okay, play them out for me.
The first horseman is work hardening. Austenitic stainless steels have a highly pronounced tendency to work harden. Meaning, as the tool pushes into the metal and plastically deforms it to create a chip, the crystal lattice structure of the metal at that exact impact zone compresses and actually gets harder.
Okay, let me try to wrap my head around the physical mechanism here. It's like kneading a ball of dough, but the harder you push on the dough, the more it turns into solid concrete.
That's a great way to visualize it.
The crystal structure is literally defending itself by packing tighter under pressure. So the first pass of the cutting tool might be fine, but when the tool comes around for the second pass, it's suddenly trying to cut through a layer of material that is exponentially harder than the base metal was 5 seconds ago.
That is exactly what happens. It's called the depth of cut line. The tool hits that hardened boundary layer and just shatters.
Wow.
And that leads directly to the second horseman, high material strength. Because it work hardens so aggressively, and because of those dense alloying elements we talked about, the sheer physical force required to push a cutting edge through this material is massive.
So everything is under more stress.
Right. The cutting forces skyrocket, putting immense strain on the machine spindle, the tool holder, and the insert itself.
Okay, horseman number 3, poor thermal conductivity.
This one is a killer. Most metals are decent conductors of heat. When you machine a standard piece of steel, about 80% of the heat generated by the friction of the cut travels into the metal chip being removed.
Okay, so the chip acts like a heat sink.
Exactly. The chip carries the heat away from the cutting tool. But austenitic steels are terrible thermal conductors. The alloy composition actually disrupts the transfer of thermal energy. So the heat doesn't escape into the chip, it gets trapped right there in the cutting zone.
It's like trying to drink boiling hot coffee out of a metal cup that has no handle. The heat has nowhere to go but straight into your hand.
Ouch, yes.
In this case, the heat goes straight into the cutting tool, baking it alive at temperatures that can easily exceed 1,000 degrees Celsius.
And that extreme heat and pressure brings us to the fourth horseman, stubborn chips and built-up edge, or BUE.
Okay, what is BUE?
Well, remember how M is the mixed group. The chips aren't long and flowing, but they aren't short and crumbly either. They're tough, stringy, and highly ductile. They don't want to break.
They just want to tangle.
Right, they tangle around the tool. Worse, because of the immense heat and pressure we just talked about, the stainless steel actually micro-welds itself to the cutting edge of the tool.
Wait, it literally fuses to it, like you're forming metallic bonds between the workpiece and the tool in real time.
Yes. The localized pressure and heat are so high that the atomic structures bond, forming a built-up edge. And when the force of the cut finally causes that little welded piece of material to break off, it doesn't break cleanly.
Let me guess, it takes a piece of the tool with it.
It rips a microscopic chunk of the cutting tool's coating away with it. If we connect this to the bigger picture, these 4 factors, work hardening, high cutting forces, trapped heat, and built-up edge combine to form a perfect storm of tool failure.
A total disaster for manufacturing.
Yeah, they wreck machining accuracy, they destroy the smooth surface finish you need for things like surgical implants, and they rapidly accelerate tool wear, especially with those heat-resistant austenitic steels, which are universally considered among the most difficult to machine materials on the planet.
Okay, so looking at all this, I just have one massive question. If the material is fighting back this hard, if it's turning to concrete, burning the tool alive, and ripping the tool to pieces at a molecular level, how on earth do the cutting tool producers fight back without just breaking all their equipment? I mean, you can't just slap a sharper edge on a piece of carbide and hope for the best.
No, absolutely not. It requires a highly systematic approach to innovation. It's about combining advanced physical vapor deposition coatings, tweaking the microgeometries of the tool edge, utilizing highly efficient fluid dynamics for coolant systems, and providing exact operational parameters.
A company called ISCAR actually provides a perfect case study for this in our source. Their specific engineering counterattacks against these 4 horsemen are wild.
They really are.
Let's look at drilling first. You have to push a tool deep into an enclosed hole in this indestructible metal. To fight back against that built-up edge where the metal micro-welds to the drill, they developed a carbide grade called IC948.
Right. IC948 utilizes a submicron substrate.
Let's break that down for a second. A submicron substrate means the physical grains of the tungsten carbide powder used to make the tool are microscopic, right? Finer grains mean a denser tool with fewer microscopic voids where cracks can propagate under high stress.
Exactly. It provides immense structural wear resistance. But the real magic against the built-up edge is the special nanolayered PVD coating on top of it. Physical vapor deposition.
You are literally vaporizing materials in a vacuum chamber to paint an atomically thin, friction-killing armor onto the tool.
Yes. This coating is specifically engineered to have an incredibly low coefficient of friction and high thermal resistance. It creates a molecular barrier that physically stops the stainless steel from sticking and fusing to the drill, even at extreme temperatures.
Okay, but what about the chips? If you are deep in a hole, you can't just coat your way out of a jam. You have those stringy, tough ISO-M chips clogging the flute of the drill.
Right, chip evacuation is critical.
So ISCAR expanded a family of tools called Quick 3 Cam for making larger holes, and they feature this specially shaped deflector. But wait, if the metal is as tough as we establish, wouldn't a tiny chip deflector carved into the cutting edge just shear off instantly under the massive cutting force?
You would think so. But this is where microgeometry engineering comes in. The deflector isn't just a bump on the tool, it is a meticulously calculated curve engineered into the rake face of the cutting edge.
Oh, so it guides the chip.
Better than that, it uses the kinetic energy of the chip against itself. As the stringy chip flows up the tool, the deflector forces it to curl at a tighter radius than the material's ductility allows.
So it breaks its own back, basically.
It essentially forces the chip to overbend and violently snap. It breaks those mixed chips into tiny, manageable segments that can easily ride the coolant flow out of the hole.
That is wild, using the material's own kinetic energy to fracture it. Now, if drilling is all about evacuating chips out of a deep enclosed hole, milling seems like it introduces a completely different problem. In milling, the tool is spinning and repeatedly entering and exiting the metal. The physics completely change, right?
Absolutely. Milling is an intermittent cut. The cutting edge smashes into the metal, heats up to 1,000 degrees in a millisecond, then exits the metal into the open air, cools down, and then smashes back in.
Sounds like torture for the metal.
It is a cycle of massive thermal and mechanical shock. Remember the poor thermal conductivity we talked about? The heat is trapped.
So how do you manage the heat when the tool is essentially going through a rapid-fire thermal shock cycle? ISCAR uses high-pressure coolant, or HPC, in milling families like Hilly Remill. But getting fluid to a spinning tool edge isn't exactly new.
Getting fluid there isn't new, but getting it to the exact microscopic contact point is the hard part. The leap in technology here is how they deliver that coolant. To get the fluid exactly where it needs to be, they're using additive manufacturing.
3D printing.
Exactly. Traditional subtractive manufacturing can only drill straight holes for coolant channels inside a solid metal tool body. But by 3D printing the milling tool layer by layer, engineers can use computational fluid dynamics to design complex, curving, organic internal channels.
So they are essentially printing a vascular system inside the cutting tool.
That's a perfect analogy. It allows for pinpointed, high-velocity coolant delivery right at the cutting zone. It blasts away the heat and the chip simultaneously, making it highly effective for minimum quantity lubrication or standard wet machining.
And we see this same high-pressure coolant logic applied to threading operations, too. ISCAR applies HPC to square shank tools with internal channels.
Threading is such a delicate operation.
Right. If a tough stainless chip wraps around the threads you just cut, it ruins the entire workpiece. By forcing high-pressure coolant right at the cutting edge, it violently cools and fractures the chip, ensuring they are short and easily managed so they don't tangle around the machine parts.
So when you step back and look at it, it's a game of microscopic margins.
So what does this all mean? When you synthesize all of this, these invisible microscopic changes, a nano-layered PVD coating here, a 3D printed internal fluid channel there, a geometrically optimized chip deflector, these tiny details are literally the only things standing between a successful flawless product and a shattered $1,000,000 machine tool.
That is exactly what it means. Machining ISO-M stainless steels is a constant, unending battle against intensive tool wear, complex chip control, and extreme heat management.
It never stops.
It doesn't. As the metallurgy of the stainless steel advances, the tooling has to advance. The only way we can keep up with the world's demand for these incredibly tough, modern austenitic materials is through unrelenting innovation from tool manufacturers.
The metallurgy gets tougher, so the physics of the tools have to get smarter.
Exactly.
And that brings us to the end of our deep dive into the hidden world of machining stainless steel.
But before we go, this raises an important question. A bit of an engineering paradox for you to chew on.
Oh, I love a good paradox.
Well, we discussed how, in order to properly cool the tools cutting these advanced metals, companies are now using additive manufacturing 3D printing to create those complex internal coolant channels inside the solid metal tools.
Right, the internal vascular system you mentioned.
So think about this. Subtractive manufacturing. the act of cutting and machining metal away, is the backbone of modern heavy industry. But are we entering an era where our ability to perform subtractive manufacturing is now entirely dependent on the limits of additive manufacturing?
Wait.
Yeah. As superduplex and heat-resistant metals get harder and harder to cut, our ability to machine them might soon rely solely on how intricately we can 3D print the very tools doing the cutting.
That is a wild thought. We literally cannot cut the metal unless we can print the tool to cut the metal. Additive manufacturing swooping in to save subtractive manufacturing.
Like a perfect closed loop of advanced engineering.
It really is. Thank you so much for joining us on this custom deep dive. We really hope this gives your curious brain plenty to think about. The next time you look at a shiny, indestructible piece of stainless steel, whether it's the sink in your kitchen or a pressure valve in a refinery, I hope you think differently about the microscopic war of physics it took to get it there. Until next time.